All right, it is 10 a.m. Good morning to everyone. Welcome to the first of our content review sessions for students and teachers for AP Calculus AB. My name is Aaron Timmons. I'm the Math Content Director for Advanced Kentucky. We are very excited that everyone has shown up on a Saturday morning to review some limits, continuity, and differentiation techniques. So we are happy to be joined by Melanie Gray, Madison Central High School in Richmond, Kentucky, AP Calculus teacher, and also AP exam reader. So as you all make your way into the session, for those of you that are just joining us, please make sure you have today's handouts right there at bit.ly/mathcrs. Make sure you pay attention to the capitalization. That should take you to a Google folder where you can then navigate to today's materials. So find the Calculus AB, then session 1, and all of Melanie's handouts will be in there as well. All right. So general disclaimer here, this online review session is intended for Kentucky audience, space permitting. We do welcome students from other areas. I know we have people from across the country, so welcome. We'll do all we can to provide every student with an equitable opportunity to learn. During today's session, we encourage participation. We'll talk about that in a second. Please know, though, any participant causing a disruption to the session will be removed. Currently, I don't think you really can cause a disruption because you should only be able to chat. Currently, you can chat with everyone in the chat room. We'll be toggling back and forth between chatting directly with myself or everyone based on the questions being posed. All right. So again, Advanced Kentucky is happy to host these for the second year. We started these last year when everything changed, and we are happy to continue them this year. So give us a follow or look us up on Twitter and Facebook at Advanced Kentucky. My email and Twitter is there. If you have any questions after today's session, feel free to tweet or email. Today, microphones, you cannot talk, you cannot show yourself, you can chat. Again, you can chat directly with me, or at times you'll be able to chat directly with everyone else. So please take advantage of these. This is the way that we want to make this as interactive as possible within the requirements of our security. So feel free to ask any question. You don't have to worry about getting called out because no one will see the question if it's directed to me, and I will keep you anonymous. I'll just say random student asks. Feel free to ask any questions, no matter how insightful you think they may or may not be. We will get those to Melanie, and she'll be happy to address those. So today's session is being recorded along with all other sessions during the rest of the school year. They will be posted to our website, which is bit.ly/advancedavky. So the same place where students went to register will be where those videos will be posted. So if you have students that were unable to view the session live, then you can have them follow up by looking there. Someone says some of their students are having issues getting in. The students do have to have an authenticated Zoom account, so they may need to sign up for a Zoom account, which is free, but that is another security feature that we've had to put in to make sure that we are getting legitimate people. So you may want to direct them to try that, make sure they are logged into a Zoom account before they sign in. Oh, and then, all right. So I'm now going to turn things over to Melanie. So Melanie, if you turn your camera on, you can introduce yourself again. Melanie is a longtime AP Calculus teacher. She is also an AP exam reader as well. So Melanie, we're happy to have you, and take things away.
Hi, everyone. So excited to see you this morning, excited for this review session. I'm going to go ahead and share my screen. I have a few slides to share with you here before we get started. So this first content review session will be over limits and continuity. And as Aaron said, I am Melanie Gray from Madison Central High School. I'm here in my classroom this morning. You can see I also adjunct for Eastern Kentucky University. So I may see some of you Kentucky students if you end up going to EKU. I'm here in Richmond, Kentucky, and my Twitter handle is @CalculusQueen. So you can see I got the Cal theme going on here. And my one corny slide of the day, we're telling COVID-19 to move over because we're chasing that 5 on the AP exam. So one Saturday a month from now until May, you will have an opportunity for these free study sessions. So on this slide, I just wanted to point out what's coming up and what we're doing today. As I already mentioned, our first session is over limits and continuity. The second session today will be differentiation techniques. We'll talk about that. Then in February, you'll see on the slide here, differentiation apps and big theorems. That's going to be the topics for February's study session. So make sure you check that out. Come back and check that out. March the 6th, we have functions and their derivatives, accumulation, approximation, and the fundamental theorem of calculus. Then in April, we have integration techniques and differential equations. And finally, in May, right before the exam, integration, applications, and area and volume. So please be sure to come back. Those are going to be some amazing review sessions. This is an awesome opportunity that I'm so thankful for my own students and for all the AP Calculus students out there. So
Melanie,
thank
you. For 1 second.
Yeah.
So not to take away from Melanie's fame, but later on, those later sessions, we're going to have some of the names you may be familiar with from your AP Daily videos. We'll have Verge Cornelius, Mark Corrali, amongst other well-known calculus presenters. So we will be excited to welcome them as well, just like Melanie.
Absolutely. So thank you, Aaron. That's a great point. So excited to see all the great calculus teachers coming up after me. So the agenda for this first session here in just a moment, I'm going to do just a short little Jamboard where I'll drop a link in the chat. And what you will do is you'll take a Post-it, a virtual Post-it, and you'll type in your name and where you're from, just so we can kind of get a feel for where everybody's tuning in from this morning. That's going to be on a Jamboard. Again, I'll drop the link in the chat. You'll click on the link, and then it will take you to a Jamboard where you will pick a sticky note and write your name and where you're from on it. Just a fun little starter activity for us so we can see where everybody's from this morning, and you'll just put your first name on there if you're comfortable with it. If not, you can just put your city. Then we'll do a little Desmos warm-up. I'm going to start the Desmos and project it on my end, and then we'll do one slide where I'll again drop the link in the chat, and you'll complete that slide on your own just as sort of a warm-up check. Next, we'll talk about just a list of things that you'll need to know for the exam from limits, and then we'll get into, of course, the guided review notes and the examples. So before I drop the link for Jamboard in the chat, I want to just show you what it's going to look like and give you a little more instruction before we jump right into that. So hopefully you're seeing my screen here. So once you click on the Jamboard, you should see this. It's a CalPrint background and a little sticky note that says add a sticky note with your first name. If you go over here to the left, now depending on your device, this menu might be at the bottom of your screen. Either way, locate this menu, and if you see this icon here that I'm pointing to, it's the sticky note icon. If you'll just press on that, and then you can type in your first name and where you're from. And we'll just take a few minutes to do that once I have shared the link in the chat. So while I'm pulling it up here, if you will locate the chat feature of Zoom, find your chat feature, and Aaron, I'm sending, looks like I'm going to send the link to you. Can you copy and paste that for me? I don't think it's allowing me to message everyone.
The settings may not be adjusting live, so we'll just have to go through me. That's fine.
Or actually, wait, I might be able to do it. Here, did that work?
Oh, there you go. Yeah.
Oh, okay. I'm sorry about that. At first it didn't give me that option, but there we go. So in your chat, you should be seeing a link to a Jamboard. And if you will click on that link, now I know some Chromebooks may not have the capability for the hyperlink, so you might actually have to copy and paste it into your browser. But for most devices, you should just be able to click on the link and it'll take you to the Jamboard. I see a lot of people are already in.
Yeah, there. When I clicked on, there are
You
currently
guys
2
are on top of it. I know when you add a, I'm moving some of yours around because when you add a post-it, it sort of covers up the post-it before you. So I'm trying to move them around a little bit for you so that you can see. I see Richmond, Kentucky, Richmond, Virginia. Shout out to Knox Central, Lexington, Kentucky. Awesome.
So this is a good problem, but we are having too many people on the Jamboard, I think. So as people fill in, yeah, we're getting a couple people. Even I clicked on the link and it said too many people viewing this file. Please try again later. So.
Oh wow, that's a good problem to have.
Yeah.
I'm very sorry for those of you that can't get in, and also if the board gets full, if you look at the top, you can arrow over and add a sticky note to a different slide. I know the board is getting kind of full here, but yeah, I'm sorry for those of you that can't get in, but it's nice to kind of see where all of you are tuning in from this morning. Shout out to Flat Lick, Kentucky. I see Georgetown, Shepherdsville. Awesome. Welcome to everyone.
You can also drop it in the chat if you are unable to use the Jamboard too, or you can do both. Yeah, feel free to put it in the chat.
Welcome, welcome. Okay, so as you're wrapping that up, I'm going to share my screen once again here. And I'm going to go into this Desmos activity, but for this first part of the activity, it's going to be on my screen and I'm going to sort of guide you through the first couple of slides. So you guys are not on Desmos yet. If you'll go back to your Zoom, so you'll come out of the Jamboard and just click on your Zoom icon so that you can get back to seeing my screen. Aaron, do you see any other shout outs we should give in the chat? I see a lot of people coming in.
Got a lot of Richmond, Barberville. I saw Denver, Chicago, Florida, Eastern Kentucky. Yeah, so all across the country. That's great.
Awesome. I see Huntsville, Alabama. Shout out to Chicago, Illinois. Welcome. Awesome. Okay, so for this first part of the Desmos activity, again, this is just a warm up because I realize that it's been probably a long time since many of you have discussed limits, or at least the basics of limits, depending on where you are in the curriculum. So I thought this would be a good place to just do a short, quick reminder of what a limit is, and then I will share the Desmos with you and have you guys complete one of the slides so that we can get a feel of understanding. So for the first slide, it says, watch this dot as it moves along the function y equals f of x. And we want to know what y value is the dot getting closer to as x approaches 1 from the left-hand side. So remember, with limits, we can think of it as what is the y value approaching as x approaches a particular c value. In this case, the c value is 1. So you're looking as x approaches 1, and the y value from the left-hand side is approaching 2, if you watch that dot. Okay, so I'm just going to submit 2 for that, and then we're going to move into the next slide here. And on the next slide, you should see we're approaching, x is approaching 1 from the right-hand side. And now my y value appears to be approaching +3. So from the left-hand side, my limit is approaching 2. From the right-hand side, my limit is approaching 3. And we all know that for a limit to exist, the left-hand side has to match up to the right-hand side. And then finally, on this third slide, it says, what is the actual value of y when x equals 1? This is an Algebra 2 question, isn't it? It wants to know what is the y value when x equals 1. So what's happening at x equals 1? And that looks to be about 0.5, right? About a half if we're estimating here. So I'm going to put in 0.5. And then finally, in this last slide that we're going to look at together, I wanted to just remind you of the notation for left and right hand limits. So notice here, if I click on the limit as x approaches 1 from the left-hand side, you see that the c value, that's the number that x is approaching, has a superscript of 1, or I'm sorry, a superscript of negative on the 1. And so illustrating over here on the graph, we're coming from the left-hand side when the superscript is negative. Now I'm going to click over to a superscript of a positive on the 1, and you can see on my graph it changes coming from the right-hand side. And finally, if I click on f of 1 equals 0.5, it's just this point at x equals 1. So the next thing that I would like for us to do is I'm going to share a link to this activity with you guys. And again, I'm going to, so I'm going to stop my share, and then I'm going to drop in the chat a link to this Desmos activity. Here we go. And if you'll click on this link, it's going to take you to a slide that I would like for you guys to all complete on your own. So the link should be in the chat now. So if you'll click on that link, it should take you to my Desmos activity, but it should take you to slide number 6 from the activity. And on slide number 6, you are asked 3 questions, A, B, and C. So I would like for everyone to try to click on the link and respond to those questions. I see we have about 77, 78, 80 students that were able to get on. Great. Great, great, great. More students coming in. So I'll give you about, let's just take just maybe 2 minutes before we talk about, yes, you can continue without signing in. Thank you. I got a message in the chat. You don't need to sign in or create a Desmos account. Just click on the box that says continue without signing in, and it will prompt you to put your name in there, and that would be absolutely fine. Yeah, you don't have to sign in. You can, but you don't have to.
And Melanie, will you include that Desmos link in your slides, maybe for people who are watching it afterwards?
Absolutely, yes.
All right.
I'll go back and put it in the document.
Right. So for those of you that are watching on demand and we are not live, check out those handouts, bit.ly/math, capital C, capital R, capital S, which is at the beginning of this presentation.
And Aaron, one thing that I noticed is I had sent you the handouts as a PDF. So I will add the Desmos link to my slides, if that's okay.
Okay, perfect.
I'll just put the link in the slides next to in the agenda.
Okay, all right, sounds good.
All right, let me share my screen now, and I'm going to just kind of go through. Now, I have changed your name so that you are anonymous. All of these names are names of mathematicians and whatnot. So I just, these are your answers with your name changed. So just to kind of scroll down through here and you guys can see, we've got some rock stars in the room, in the virtual room this morning. -1, 2, and 2. Looks like most of you are agreeing on this answer, right? So let's go back. Those are your responses. So let's go back and see from the left-hand side. I would have to agree with you. We are approaching -1. From the right-hand side, we're approaching 2. And then for part C, the actual y value is this closed circle at +2 as well. Okay, so you guys can get out of that Desmos activity. And now we're going to move into the handout. That is the student handout. And we're going to get into some of the review notes. Let me share my screen again here from my iPad. There we go. So hopefully now you're seeing my student handout for limits and continuity, and we're going to dig into some of the examples for limits right after we look at a list of things that we need to know. Yeah, I see in the chat real quick, I'm getting a request to drop the link again in the chat for students that came in late. Absolutely. Oh, let me see here. I will drop it again now. There you go. All right, so back to our list of things that we need to know for the AP exam concerning limits and continuity, things that we're going to discuss today, of course. So how to determine limits from a graph. That's where we're going to start, looking at a graph and finding the limit. Then we'll go into a couple of examples of how to compute limits algebraically. Moving on to how and when to apply L'Hopital's rule. And then time permitting, I think we'll wrap up this session with how to lose limits to determine if a function is continuous at a point. And we'll begin the next section because I think it's a good segue into differentiation and how to recognize the limit definition of a derivative. Okay, so that's kind of the bridge between this session and the next session. So let's start with determining limits from a graph. And I'm going to try to zoom in here on mine so you can see it a little better. Determining limits from a graph. So a couple of things I need to remind you that you may want to jot down. Hopefully you're taking notes. One thing you want to jot down is for a limit to exist, you know, at a particular point, you know that the left-hand limit as x approaches that c value must equal the right-hand limit as x approaches that same c value. If the left and the right-hand limits are equal, that is your actual limit. Now, another thing I may want to remind you about is when a limit does not exist. So of course, if the left-hand limit and the right-hand limit doesn't match up at that particular X value or C value, then you want to say that that limit does not exist. Also, if there's a vertical asymptote or the case of an oscillation. So those are some things just to remind you of that you may have talked about back in Unit 1. So let's look at this example 1. It says the limit as x approaches 1. Notice that superscript of a negative from the left-hand side. So if we're coming from the left-hand side, I'm going to draw my arrows on here. Coming from the left-hand side of 1, and also let me highlight 1. I'm looking at 1 on the x-axis. So as I'm approaching 1 on the x-axis, my y values appear to be going to +1 from the left-hand side. And then if we come in from the right-hand side, so if I'm coming in from the right-hand side of +1 on the x-axis, my y value is constant and is approaching +2. And then finally, part C says, okay, well, what is the limit as x approaches 1? And as we just said, if the limit from the left-hand side is different from the limit on the right-hand side, then we know that limit does not exist. The limit does not exist. And then for part D, we want to know what is f of 1. Well, f of 1 is the Algebra 2 question I always say. What is the y value when x equals 1? The y value when x equals 1 is this closed circle at 2. All right, let us know in the chat if you have any questions about that little review before we look at some multiple choice items. I'm going to scroll up here to number 2 from the handout. On number 2, it says, for which of the following does the limit as x approaches 4 exist? Now look at your answer choices. You've got 1 only, 2 only, 3 only, 1 and 2 only, 1 and 3 only. So if you look at Roman numeral 1, we can see that as x approaches from the left-hand side, the limit is, the y value is approaching what looks to be about 3. So from the left-hand side, it looks to be 3. And then from the right-hand side, the y value is approaching 3. Now I know there's a hole there and there's a point above, but we're looking to see what y is approaching. And in both sides, the limit is approaching 3. So Roman numeral 1 is a yes. If you look at Roman numeral 2 coming from the left-hand side, it looks like on this one, the y value is approaching 4 from the left. And from the right is also approaching 4. So even though the y value does not exist at 4, the limit does. So that one's a yes. And then finally on number 3, if we're coming from the left-hand side, it looks like the y value is approaching 4. And from the right-hand side, the y value is approaching 2. So we know that this one is a no, since the limit as x approaches 4 from the left-hand side of f of x is not equal to the limit as x approaches 4 from the right-hand side of f of x. So our answer on this one should be D, 1 and 2 only. So remember on the AP exam, it's important to look at your answer choices. Notice how I did that before I started in on the actual problem, because if you have a problem like this, well, you don't want to look at the first one and say, oh, the limit exists on number 1, and then just get in a hurry and mark A and move on. Because while 1 is true, 2 is also true. So we want to make sure that we choose answer choice D. And then Aaron, I think we have a poll for number 3 on this one that I'd like for them to try this one on their own. Number 3 from the handout.
So we do have the poll. So do you want to give them a little bit of time, because I know some people's screens, once I throw up the poll, it blocks the question. So
Oh, sure. Yes, absolutely.
so let's take like a minute or so, at least get the question read and come up with your best guess, and then I'll throw the poll up for you all to respond. All right, so I'm going to throw the poll up. Again, you can move the window out of your way if you need to. Poll is anonymous, so please take a moment to respond when you have the chance.
Looks like they have about, oh, is that counting down?
It's counting up.
Oh, I'm sorry. I thought they had 20 seconds. I was going to give them a warning. I'm sorry.
We'll take like maybe 30 more seconds to respond. We've got about 70%, 75% in. All right, I'm going to end the poll. There are the results. Oh, let me share. Here are the results, and Melanie, you can discuss those results, and then I'll take them off the screen.
Absolutely. So again, the answer was C. So you guys, most of you were right on track. A few answers. Let's see, it looks like maybe one answer for A, a couple answers for B, D, and E. But let's go back to the question and let's talk about why the answer was C. So on this one, it says the figure above shows the graph of a function f with the domain x between 0 and 4. Which of the following statements are true? So statement 1, the limit as x approaches 2 from the left-hand side. So I'm going to highlight that in red, and I'm going to use red up here to show you that from the left-hand side, my limit does exist. Now, even though there's an open circle there, let's pretend that there are values marked on the y-axis. So let's say those values were on the y-axis. Then coming from the left-hand side, we would say the limit is approaching 2, even though there's an open circle there. The limit is what the y value is approaching, not what the y value is at that point. So the y value is approaching 2 from the left-hand side. And then from the right-hand side, I'm going to highlight that in green. And so I'm going to use green arrows up here. From the right-hand side, this piece is constant. It looks like that is approaching 1, or it actually is 1 because it's constant. And so that certainly exists. So we can put, we can say 1 is true, and then 2 is true, and then 3 is not true. So the reason that 3 is not true is, again, because for the limit to exist, the actual limit as x approaches 2, the limit from the left-hand side of f of x has to equal the limit on the right-hand side of f of x. And in this case, it doesn't. With the y values that I've added there, you have from the left-hand side, we're approaching 2. From the right-hand side, we're approaching 1. Since those values are different, the limit does not exist as x approaches 2. So this answer would indeed be C. Thank you guys so much for participating. Awesome job. High five for everyone that participated there. Don't feel bad if you got it wrong. That's why we're here. We're learning. We want to get things wrong now so that when we get to that AP exam, we knock it out of the park. All right, moving on to computing limits algebraically. So we first talked about computing limits graphically. Now we're going to look at computing limits algebraically. And I'm actually going to write over here in this blank space a little bit before we dig into these examples. So the first thing that you should try when you're computing limits algebraically is direct substitution. And if you get a constant when you try direct substitution, that is your limit value. However, I do want to point out that if C is a non-zero constant, so it's any constant other than 0, if you do direct substitution and you get 0 divided by C, that means your limit is equal to 0. Okay? If you get a constant divided by 0, then that means your limit does not exist. But if you get this 0 over 0, which we call indeterminate form, if you get 0 over 0 and you're computing limits algebraically, in my classroom, we say that means more work. And by more work, we mean you could do something like factoring, or you might do common denominator. You might have to multiply by a conjugate. Those types of simplifications with trig functions, you might have to convert everything to sines and cosines. Now, a little bit later here in just a few minutes, we're going to talk about when you get 0 over 0, you can also do something called L'Hopital's rule. But in this little section of our notes, let's focus on computing the limits algebraically using one of these techniques. So looking at number 4, we have the limit as x approaches 4 of this rational function x squared minus 16 over x minus 4. So if you sub 4 in for x, you're going to get 16 minus 16 on top, which gives us 0. So I'm going to write the limit as x approaches 4 of x squared minus 16 gives us 4 squared minus 16, which is 0. And then separately, I'm going to write the limit of x minus 4, the denominator, is 4 minus 4, which also gives us 0. Now, this is important for you guys if it shows up on the free response portion of the exam. You never want to write that this limit, I even feel like I shouldn't write it down on these notes, but you never want to write an equals 0 over 0. Okay, even though when you sub in 4, you get 0 on top and you get 0 on bottom, you will lose points on the free response portion if you say the limit equals 0 over 0. So I'm trying to model for you here if this were to show up on a free response, something like this were to show up on the free response L'Hopital, then you would want to write out the limit as x approaches the numerator in one line and the limit as x approaches the denominator in a separate line. And once you have each of those equal to 0, you know that you can use L'Hopital's rule. When, again, I'm sorry, I'm kind of going back and forth here because we are going to get into L'Hopital's rule here in a minute, but we're going to use factoring on this one. but I just wanted to make that point that when you are working out a problem, you never want to write that the limit is equal to 0 over 0. Okay, so once you establish though that when you do use direct substitution, you get indeterminate form, then you can move on with your algebraic computation. So let's do that here. I'm going to go back and say this limit as x approaches 4, and I'm going to factor the numerator. It's going to factor to be x plus 4 times x minus 4 on top, and then we have an x minus 4 on the bottom. And so I can divide out those x minus 4s, and I'm left with the limit as x approaches 4 of x plus 4. Use direct substitution to sub that 4 in for x, and then we get 8 for our limit. All right, and then if you will look, I'm gonna skip number 5 for now. This is another one. I'll just briefly talk about it, just because I don't want to run out of time. If you put 0 in for x here in number 5, you'll see that you do again get 0 over 0. And this is one that you can do with a common denominator. So you can get a common denominator in the numerator and work through that problem. If we have time today, I'll come back and work this one for you, but I want to make sure I give you at least one example of each of the topics. So let's go on to talk about horizontal asymptotes for just a minute, and if we have time, we'll come back to that. Okay, so with the horizontal asymptotes, what you want to remember is in a problem like number 6, 7, or 8, notice how you're taking the limit of 3 rational functions. So in number 6, 7, and 8, one thing that you want to be able to recognize is that in these cases, when you take the limit as x approaches either positive or negative infinity, you can use those horizontal asymptote rules from Algebra 2 as a shortcut for these. And now you might be saying, what horizontal asymptote rules are you talking about? So I'm going to remind you, and if you have, in my class, we do a yellow sheet where we add all of the things that we have to memorize. So if you have one of those sheets that you've been using for your class, you may want to add this on if you don't already have it memorized. It's just a really quick and easy way to evaluate a limit as x approaches positive or negative infinity of a rational function, like in example 6, 7, and 8. So for the horizontal asymptote rules, you want to remember that if the degree of the numerator, I'm going to abbreviate numerator, is greater than the degree of the denominator, I'll abbreviate denominator, then we know the horizontal asymptote, it doesn't have a horizontal asymptote, so that means the limit does not exist. But if the degree of the numerator is less than the degree of the denominator, then in that case, your horizontal asymptote occurs at 0, and that means the limit equals 0. And finally, if the 2 degrees are equal, the degree of the numerator is equal to the degree of the denominator, you're going to divide the leading coefficients. So divide what we call the leading coefficients. Now remember, the leading coefficient is the number in front of the variable with the highest exponent when your answer is written in standard form. So divide the leading coefficients, the leading coefficient of the numerator divided by the leading coefficient of the denominator. So let's look at some of those examples. So look at number 6. Number 6 says the limit as x approaches infinity of 3x squared plus 2x minus 4 over x cubed minus x plus 1. We want to compare the degree of the numerator, which happens to be 2. The highest power on the variable is 2. That's the degree, in case you've forgotten. And the degree of the denominator is 3. Again, the degree is the highest power on the variable when it's written in standard form. So the degree of the top is smaller than the degree of the bottom. So that means this limit is going to be 0. Then for number 7, we have the degree of the top is 2. The degree of the bottom is also 2. So the degrees are equal. So in this case, if the degree of the top is equal to the degree of the bottom, this is where we divide those leading coefficients. And so we say that the leading coefficient of the numerator is 4. The leading coefficient of the denominator is understood to be 1. It's the number in front of n squared there. So our limit is 4 on that one. And then I believe we have another poll coming up on number 8, where I'd like you guys to try this number 8. So if you'll take a moment to write this one down, or hopefully you have your handout in front of you. I'm going to ask Aaron to put the poll up for this one after they've had just maybe a minute to look at it and do some work here.
Will do. And again, as you work, if you have questions, stick them in the chat and we will get those answered for you. All right, so we will launch that poll right now. Again, you can drag that window out of the way if you're still working. About 57% of responses. So let's try to get that up closer to 70, and then we will proceed. All right, we've crossed that. So I'm going to end the poll here, where we've got about 75% responding. So here are the results.
Great, thank you. It looks like you guys, the majority has the correct answer here. The answer for this one was B, -2. Several people had also chosen C, which is very close. You just had the positive version of the answer. So let's go back to number 8 and let's talk about why the answer was -2. So on this one, you could do it without multiplying it out. Of course, you know, when a rational function is in factored form, you can find the degree by adding together the degree of each factor. So we know this is a degree 2 over degree 2. So we know the degrees are equal, and we're going to have to divide the leading coefficients. It might be a little bit easier to see if we do go ahead and multiply it out. So if you multiply, oops, sorry about that. If you do multiply this one out, you can distribute the 2x to the 3 minus x, and you're going to get 6x minus 2x squared, and then we can distribute the -1 to get -3 plus x, and then in the denominator, distribute your x, you get x squared plus 3x, and distribute your -1, you get -1 minus, or I'm sorry, -x minus 3. And so if you're looking at the degrees, you can see that the degree is, the highest power is 2 in the numerator and in the denominator. And then the leading coefficients would be -2 here, the number in front of the variable with the highest exponent. And then here would be understood to be 1. So you could do -2 over 1, which would give you -2.
All right, Melanie, we have our first question.
Okay.
So this is more of an AP exam question, but someone asks if the AP test counts off for incorrect answers, or is it similar to the ACT where it does not count against you when you guess?
Oh, great question. So for the multiple choice, it does not count against you when you guess. So great question. Thank you for asking that. I'm sure there's many people out there asking or wondering the same thing. So it will not count against you for guessing. All right, now I started talking a little bit about L'Hopital's rule back when we were doing computing limits algebraically, when we were talking about that indeterminate form. So I want to revisit that here with example 9. You can see that when you do direct substitution with number 9, we've already shown the work for that. You want to take the limit of the top, you get 0, the limit of the bottom, you get 0. So if you get indeterminate form 0 over 0, or really any indeterminate form, but for Calc AB, we're looking at 0 over 0. Then you can do L'Hopital's rule, which says that if you take the limit as x approaches 4 of f of x over g of x, when you do direct substitution, well, I shouldn't say x approaches 4, should I? X approaches c of f of x over g of x, any number, doesn't have to be 4, then you can set that equal to the limit of the derivatives. Okay, so if you get indeterminate form, then you can use L'Hopital's rule. All right, and so we've already talked about the fact that we did get indeterminate form on number 9 is the same as example 4. So this is the same function that I used in number 4, but we're going to now use L'Hopital's rule. So if this were a free response item, you would want to do like I did on number 4. You would want to take the limit of the numerator, show that it equals 0. The limit of the denominator, show that it equals 0. And then you can say that this limit is equal to the limit as x approaches 4 of 2x over 1. Since the derivative of the numerator is 2x, the derivative of the denominator is 1. And now we can do direct substitution. We get 2 times 4, and that gives us 8. Now, the reason I wanted to do that same problem again is I just wanted to show you, hey, look, we used a completely different method, And if we go back up to number 4, check it out. We got the same answer, right? We still got 8, no matter which method that we used for that one. But here's what I was talking about for if you were doing a free response item where you were applying L'Hopital's rule, you really want to make sure that you never say equals 0 over 0. You want to show that the limit of the numerator equals 0 and the limit of the denominator equals 0 separately. And then you can go straight into L'Hopital's rule once you've made those statements. All right, let me move ahead. I know I'm running low on time. I want to get in at least one of these free response items dealing with continuity. So let's fast forward to, in my handout, it is page number 7. We have a function is continuous at a point A if and only if these 3 things are true. So I want you to write these down with me. Now in Algebra 2, we think about continuity that we can draw a graph without picking up our pencil, right? In calculus, we have a much more formal definition of continuity at a particular point. And we say that it's continuous. The function is continuous at A if and only if, first of all, f of A exists. Then we say if the limit as x approaches A of f of x exists. And then finally, if the limit as x approaches A of f of x equals f of A. So on a free response item, these are the 3 things that you must show if you're trying to prove continuity. If you're trying to prove that a function is continuous, you want to make sure that you've covered these 3 bases to get all of the points. All right, so let's fast forward to a free response item, which is on, let's see, it's page 8 in the handout. Number 13. And I'll show you how to answer this question to snag all the points on the AP exam. Okay, so it says let f be a function defined by f of x. You have a piecewise defined function with 1 minus 2 sine of x on top, and then e to the negative 4x in the denominator. The first equation is true when x is less than or equal to 0, and the second equation is true when x is greater than 0. So we want to show that f is continuous at x equals 0. So we want to show those 3 things that we just discussed are true. So the first thing that we said is that f of A has to exist. So our A in this case is 0. That's the x value that we're interested in, x equals 0. So our A value that we're talking about is 0. So we want to say that f of 0 equals 1 minus 2 sine of 0. I'm using the top equation because if you'll notice here in the constraint, it says x is less than or equal to 0. We use the top equation. If it's greater than 0, we use the bottom equation. So we do 1 minus 2. Sine of 0 is just 0 from our unit circle. This is a non-calculator problem. So you want to make sure you know those values from the unit circle. So we get that f of 0 equals 1. Well, because f of 0 equals a number, we have shown that it exists. So that takes care of the first piece, that f of A must exist. It does. And then we need to show that the limit exists. So we're going to do the limit as x approaches 0 from the left-hand side of f of x. And we're going to sub into that same equation, since from the left-hand side, you're looking for that less than symbol. And that's going to give you 1. And then from the right-hand side of 0, we're going to sub into that bottom equation for x. From the right-hand side, you're looking at this greater than symbol for the right-hand side, and that gives us e to the 0, which again is 1. So since the left-hand limit is 1 and the right-hand limit is 1, we know the actual limit as x approaches 0 is 1. And that shows that the limit exists. So we have 2 pieces of the 3 that we have shown. And so finally, we just need to make sure that we state that the third piece of criteria is met. So the limit as x approaches 0 of f of x does in fact equal the limit, or I'm sorry, not the limit, but f of 0, which they all are equal to 1. So this is a good way to write your response on a free response on the AP exam, showing that a function is continuous. Sometimes they might ask you, is it continuous? So this is a good way to show, to prove or disprove that a function is continuous at a particular point on the AP exam and snag all those points possible. Aaron, I see that I'm a little bit, I'm right at 11. So do we want to take a break here before we move into this next session? I've got a few questions in the chat that I can either address to the group when we get back, or I can private message them.
Why don't we, this seems like a good time for a break. I've got a couple questions too that have come up. So why don't we take about a 5 to 7 minute break for people to do what they need to, and then you can answer questions during this break time for those that want to stick around because they know they've got one. So yeah, everyone else, if you're good, you can go and take a little bit of break. We'll commence in about 5 to 7 minutes, and then everyone else will pose some questions. So Melanie, do you want me to ask the first question, or do you have questions that you want to reply to?
No, you can go ahead.
All right, so the question here that relates to this question is, do students have to show the limit from the left and the right, or can they simply state the limit as x approaches 2 is equal to 1, since we technically found the left side limit in the first condition?
Which question is this? I'm
The one
sorry.
you just finished doing, the one you just finished working.
Oh, so did they mean as x approaches 0 then?
Oh, I think so. Yeah.
Okay, so you do need to consider both the left and the right-hand limits, because sometimes on the AP exam, they will give, you know, on the, you know, the reader's notes, they'll split the points for this particular question. And I've seen that some of the time, one of the points is that you actually consider the left and the right-hand limits. So I would say you would need to explicitly write those down.
And I know you can't see the question written, but the first condition that you did was actually not the left side limit. That was the actual function value. So that technically does not count as the left side limit. So that would be another reason why you would need to do both the left and the right side.
Gotcha. Okay. Yes, absolutely.
Another,
Somebody asked me, can I do this one real quick?
Yeah.
They were asking me to drop in the chat what the 3 things were. And I can do, I was just going to address that person and tell them I will do that.
Yeah.
I can drop that for everyone.
Right. And then someone else would like you to discuss rules related to E, but I figure that may come up in your differentiation section.
For taking the derivative of E, is that what?
So they just said discuss rules related to E. So yeah, you can cover that in the differentiation session coming up next.
Okay.
And then the last question, which is really, I feel like it's probably from a teacher, but maybe not, because I know there's a lot of students that are very good self-advocates for themselves, but they want to know if you have any tips for students with ADHD or dyscalculia. So math specific learning disabilities or ADHD, if you have any tips based on your teaching experience. There's other teachers in here that would like to voice their opinions or suggestions. They can put those in the chat as well. But Melanie, I figured you might have some ideas based on your experience.
I'm just trying to think off the top of that one. Kind of took me. I don't
I
know.
And it's actually, it actually is a student that is asking for themselves. So that's, I think, a really good thing that they're advocating for what they can do to better themselves.
Yeah, I would say just based off my teaching experience and just thinking, the more you can organize your notes, and I have mentioned that about my students always, they have a yellow sheet that they add everything to, that I tell them, okay, you have to know this for the exam. And as we go through the year, they keep adding to this yellow sheet. So they keep this sheet that's has all the information that they need to memorize for the exam. And so I'm hoping that they've already started making note cards from that yellow sheet. And so if you can organize your notes and then get them onto index cards, and then, I mean, starting yesterday, actually, just going through those note cards to help with memorization, I think, let me stop this share here. I think that would be really helpful to keep, maybe to keep a bit of the focus. I know when I forget something, I lose focus very easily. So if I have it memorized, that might be helpful. That's one thing I can think of that I would suggest, specifically because there's so many things you have to memorize for this exam. I don't know. Do you have a better suggestion, Aaron? I don't know. I don't know if that was helpful.
I think the organization, I think, and then like just the, you know, the chunking and breaking things up into smaller pieces, like you had mentioned. Those are what I found best work for students in my class. You know, they would be very good at organizing things and then just going back and reviewing those. And then also, you know, especially, and this may be helpful because we have videos now, not trying to watch this video in one sitting, you know, break it up into smaller times so that they can then kind of process and go back and work a couple questions that go along with what you just talked about, rather than trying to watch the entire session at once and working through, because that can be overwhelming.
Yeah, that's a great point.
Yeah, and the student says it's the numbers that I think that are overwhelming to them. So, I mean, that's very understandable. When you have all the numbers coming in from all different directions, I think trying to break it down into smaller chunks of time and attention, I think would be helpful. All right. So, and the person that asked about E was really referring to when E is equal to a certain value. So I replied back saying that, you know, E raised to a power would be the same as any other constant raised to a specific power. But okay. And they said that was what they needed. So.
Oh, perfect. Okay, awesome.
All right. So 2 minutes. We'll start back up at 11:10. Will that work?
Yep, that sounds good.
All right.
I'm just going to get my stuff set up here.
So those of you that are waiting here as Melanie gets prepared for the next session, just a couple general announcements. Again, this recording will be posted to our website, bit.ly/advky, the same site you used to register for this session, so that students that were unable to view it can go back and watch. Also, we have sessions for all AP Math, Science, Computer Science courses. So if you are also in an AP Biology, Chemistry, Physics 1, Environmental Science, BC Stats, CSP, or CSA, then check out our website for those dates. We have them going on all through the end of the school year. So again, those recordings will be posted. If you are an AP Lang Lit or Seminar student, we will have special sessions for those later on in April. So again, we are supporting all AP Math, Science, English, Computer Science students. Again, please spread the word to fellow colleagues, teachers. Give us some shout outs on Twitter, Facebook. Please help spread the word, especially if you are finding today's sessions to be helpful. We want to really make sure everyone is aware and can take advantage of what we're providing. We do have Physics 1. We will have sessions for Physics 1. Unfortunately, we do not have social studies or foreign language sessions. Today's physics review session is starting now. I think it's this. Oh no, sorry. I think it's also going on at the same time. It's also going on from 10 a.m. to noon Eastern time. So if you had to pick and choose sessions today, the ones you were not able to attend live will be posted those videos to the website. And then if you would like to see solutions to questions that were not gone over by Melanie because of time, those solutions will not be posted. However, you are more than welcome to reach out to Melanie or myself for specific solutions if you would like those. And we can get you or check your answers, however you'd like to do that. We can get those for you. All right, and Melanie, whenever you are ready to resume, we can start with our differentiation techniques. So I will just wait for you.
All right, I'm all good.
All right.
So let me share my screen here. So as Aaron mentioned, we're moving into differentiation techniques. And I mentioned at the beginning that a good way to segue into differentiation is to look at the limit definition of a derivative. So that's kind of where we'll start today. After we talk about what we're reviewing in this session, we'll do a little warm up and then go into the guided review and the notes. So here are the things that we'll be reviewing in this session. As I mentioned, recognizing the limit definition of the derivative, the general derivative rules, the trig derivative rules, and then implicit differentiation. Of course, there are many other rules that you guys will need to make sure that you know. Just these are the ones that I've narrowed it down because we have such a short amount of time here. These are the ones that we'll be focusing on in this session. So here's your warm up. We're going to do another limit problem. We're going to determine this limit algebraically. And so you're finding the limit as h approaches 0 of the square root of x plus h minus the square root of x all over h. And we want to find that algebraically. Okay, so if we do direct substitution here, you'll see that when you sub in h or 0 for h, you're going to get 0 in the numerator and of course 0 in the denominator. So when you're computing algebraically, that means more work. And in this case, I showed you an example of factoring. We didn't quite get back to the example of getting a common denominator, but this example is one of multiplying by the conjugate. So let's do this one together. Let's work this one together. Find this limit algebraically. So for this limit, the first thing that I'm going to do is I'm going to multiply by the conjugate of the numerator, which means I'm going to change the sign in the middle to a plus. All right, so I'm going to come over here and I'm going to say the limit as h approaches 0 of this square root of x plus h minus the square root of x all over h. And I'm going to multiply the numerator and the denominator by the conjugate of the numerator. And I'm doing this because when I tried direct substitution, I got indeterminate form. And we're asked to compute this algebraically. So numerator and denominator by the conjugate of the numerator. So we're going to do some algebra here. We're going to take the limit as h approaches 0. And when we multiply our numerators together, we're going to use the distributive property. But notice, since they are conjugates, when we multiply, first of all, when we multiply square root of x plus h times the square root of x plus h, we're going to get just x plus h. But I also want to point out, whenever we do the square root of x plus h times the last term, when you're doing FOIL, you think of it as the inside and the outside terms. That would be the outside, and this will be the inside. Notice that these are the same. Square root of x plus h times the square root of x times the square root of x plus h. Those are the same, with the exception of one being negative and one being positive. So hopefully you remember from Algebra 2, anytime you multiply conjugates together, the outside and the inside terms are going to cancel because you're going to have one positive and one negative. So I'm not even going to write those down. I'm going to now multiply this negative square root of x times the square root of x on the end. And I get negative x. And I'm going to divide that by h times the conjugate. All right, so in the numerator, you can see that your x's are going to cancel. Positive x and a negative x leaves us with just h in the numerator times the h times the conjugate in the denominator. Oh, I'm sorry, that went off the page a little bit. So in this case, the h's are going to divide out, leaving us with the limit as h approaches 0 of 1 over the square root of x plus h plus the square root of x. And now we're ready for direct substitution. We can put that 0 in for our h. Once you do direct substitution, you can drop that limit. And we end up with 1 over the square root of x plus 0 is just the square root of x. And then the square root of x plus the square root of x is just 2 square roots of x. So that's our answer, 1 over 2 times the square root of x, computing that limit algebraically. Now, hopefully some of you noticed that this particular limit was, in fact, the limit definition of the derivative. So we're going to move into our handout now. We're going to look at page 3 in the handout. I'm going to stop share on this and
Quick question there, Melanie. Someone wants to know, do they need to rationalize?
You do not need to rationalize here. You can leave it as 1 over 2 square root of x.
And I'll just add in for free response questions, unless you need to for the remaining part of the question, you should probably never rationalize. Is that fair?
Yeah, that's great.
Okay.
Great point. All right, so here's where we should be, the limit definition of the derivative. And again, this is page 3 in your student handout. And you can see I've given 3 versions here of the limit definition, but the first version is the limit definition for f prime of x. Okay, and then these two would give you the limit definition at a particular point. So f prime of c for each of these versions of the limit definition. And then I just gave you 3 examples here so that we could sort of match up which limit definition of the derivative you would need to recognize to be able to solve this problem much easier than doing something like we did in the warm-up, like multiplying by the conjugate, now that you know how to take a derivative. So I'm going to use my highlighter here, and I'm going to highlight this first function, or first limit, first example. Limit as x approaches 4 of sine of x minus sine of pi over 4 all over x minus pi over 4. Now, if you look at the 3 versions, you might notice that the first thing that really sticks out to me is the denominator of my example. It's x minus pi over 4. And in the first 2 definitions, you can see that we have an h in the denominator. But the third version here has x minus your c value, right? So if you recognize that, you can see that it's the third version of the limit definition. And I might also add here that some textbooks will use delta x in the place of h. So let me say that really quickly for some of you that may be used to using delta x instead of h. So like on this first definition, you may be used to seeing it with a delta x, and that's okay too. You should be comfortable either way, really. Familiarize yourself with both expressions. So back to example 1, if you look there, I can tell straight away that my f of x function is going to be sine of x. And the way I know that is that I look at my version of the limit definition, and I really look at this first piece of the numerator. That's where my f of x is going to be. And if you come over here to your example, you'll see it matches up to sine of x. And then I also note that my c value is pi over 4, and I really look either at what x is approaching, or you could also look at your denominator. You could also look at the second term in the numerator, but you can see that pi over 4 happens in all 3 of those places. So if we have that f of x is sine of x and c is pi over 4, what we want is we're wanting f prime of pi over 4, right? And now that you guys have studied derivatives, you know what the derivative of sine is, and you can sub that c value into the derivative. And so when you see a problem like this on the AP exam, this big, beautiful limit formula that they're asking you to take the limit of, they're wanting you to recognize it as the definition of the derivative. And so what you're going to do is just take the derivative of f of x, which is cosine of x, and you're going to evaluate it at x equals pi over 4. So you're just going to sub in pi over 4 in the place of x, and we know from the unit circle that value is square root of 2 over 2. All right, now if you'll look at number 2 with me, I think number 2 is a little bit harder to see than examples 1 and 3. But if you look closely to example 2, you can see that this function or this limit has an h in the denominator, a single term in the denominator, a variable. So looking at the 3 versions, I know it's going to be either version 1 or version 2 here. I know that according to my version number 2, if you look here, I know that f of c is this going to be the constant in the numerator at the end. So this is my f of c. And then this is f of c plus h, which you can see here. So the f of c is when you've actually taken c and you subbed it into the function. And then the c plus h, it's a little bit easier to see, or a whole lot easier to see really in this f of c plus h, that your c term is going to be 2. And that makes it a little bit easier to determine what f of x is. If you know that c is 2 by looking at this c plus h here, c has to be 2, then you can think about, well, what would f of x have to be for f of 2 to be 8? And then you can look at this first piece that I've circled, and you can see, well, c plus h looks like it was substituted into x cubed. And that makes sense because 2 cubed is 8. And what we want here is we want f prime of 2. Again, this is derivative at a point. And so we know f prime is 3x squared. We're going to evaluate that at x equals 2. So 3 times 2 squared would then give us 12. All right, let's look at number 3. Now I'm going to zoom out a little bit. I know it's kind of small, but I want you to be able to see the limit definition and the example in the same frame here. So hopefully you have your handout in front of you. So this third example is the limit as h approaches 0 of this expression involving tangent. And again, we know it's either the first or the second definition because the denominator is just h. And it's actually going to be an example of the definition f prime of x. And I can see that by looking, if you look here, this is your f of x function. The last piece of the numerator. And of course, this would be your f of x plus h, which just means you take x plus h and sub it into f of x. And so if we know that f of x is tangent of 3x, and we want, in this case, we just want f prime of x. This is just the derivative, not the derivative at a point. Then we're going to have to do chain rule here, which we'll talk a little bit more about chain rule here in a second. But let's go ahead and do this one for those of you that have chain rule fresh on the brain. You take the derivative of the outside function, derivative of tangent is secant squared. You leave the inside function alone because it's f prime of g, and then you chain on the derivative of the inside to the end, the inside function being 3x. So the derivative of 3x is just 3, and we can rewrite that as 3 times secant squared of 3x, which gives us answer b in this case. Now that we've talked a little bit about recognizing the definition of the derivative, let's look back at that warm-up problem. Okay, let's look back at that warm-up problem.
And can I ask one question real quick?
Sure.
So I think you touched on it a little bit, but can you elaborate as to why you'd want to use the second option over the first one for question 2 that you had worked? Like, what would be the difference? Because they looked very similar.
So on question number 2, notice that your f of c, so your c value up here, get my highlighter. This value here is a constant, right? In the numerator, that's a constant. So you have taken the c value and subbed it into the function. That's sort of how I see it. Whereas in number 3, this is a function of x. You still have a variable in the numerator in that position there. And also, I could point out this inside parentheses here, we have a constant plus h versus x plus h in number 3. Does that help at all, Aaron?
I think so. I think that the big thing would be the answer that they want for question 2 is an actual constant value versus in question 3, the answer they're wanting is the derivative just in terms of x also. Would you agree?
Oh, absolutely. Yes.
Yeah. Okay. Yeah.
I thought you were asking me how to recognize it by just looking at
I think that, you know, because they would say, oh, well, why wouldn't I just use option 1 for number 2? Because it looks really, you know, basically the same.
Gotcha. Absolutely.
The expected answer at the end would also be a little different. Yeah. Okay.
For sure. Okay, so let's look now back at the warm-up. Okay, so on the warm-up, we had the limit as h approaches 0 of the square root of x plus h minus the square root of x all over h. Now, if we have the chat feature active, could I ask you guys to respond in the chat if you think that I should use the blue, green, or pink version? So version 1, 2, or 3. Are you guys able to respond in the chat? I see a couple people responding to me directly. Thank you for that.
In the 2, you see if you can change the drop down and see if you can select everyone now. There we go. All right.
Awesome. I'm just looking, I'm watching questions or answers coming in. I have several coming directly to me, and then you can see some people are responding to everyone.
Got a lot of 1s coming in.
Yeah, a lot of 1s coming in. Very good. It is indeed 1. I saw a couple of 2s, and that goes back to, again, what we were just talking about, that this last piece of the numerator, that being an expression as opposed to a constant, that tells us we're going to use version number 1. So what we want is f prime of x for this one. So if we want f prime of x, we first need to identify f of x, which I just did by highlighting it. F of x is the square root of x, which we can write as x to the 1/2 power. And if we want f prime of x, you just take the derivative and you get 1/2 x to the negative 1/2 using power rule. And then with a little bit of tweaking using algebra skills, making a negative exponent positive by moving it to the denominator, and then changing that 1/2 power back to the square root. Check it out, my friends. We get the same answer that we got doing all that conjugate business back in the warm-up, 1/2 square root of x. Same answer as we got in the warm-up. All right, so let's move on to some of the derivative rules. So the next page of your notes, you have, as I mentioned, I focused in on like the general rules, the trig derivative rules, and then we're going to do some implicit differentiation. So let's go ahead and fill in some of the derivative rules that we know, starting with the constant, where you have the constant k times f of x. K is just a constant in this case. When you take the derivative of k times f of x, this rule says you can pull k out to the front and take the derivative of f of x. Then we have a rule says that if you take the derivative of two functions being added or subtracted, you can take the derivative of each piece, take the derivative of f of x and add or subtract that to the derivative of g of x. Remember that works for addition and subtraction, but not for multiplication nor division, which we'll get to in numbers 4 and 5. But first, let's do power rule on number 3. Remember, if you have x to some power n, you can pull that exponent out to the front and subtract 1 from the exponent. That's power rule. Then for product rule, there are a couple different versions out there. I'll tell you what I usually do is I do gf prime plus fg prime. And I know a lot of textbooks do fg prime plus gf prime, but I like to introduce it this way simply because the quotient rule, which is the next line, the quotient rule is going to use that same expression, just subtraction in the numerator. And so we have gf prime minus fg prime over g squared. And the way that I have my students remember it is I think about f of x as being my high function, g of x is my low function, and we sing low d high minus high d low over low low. And what that means is the low function, g, d high is derivative of the high function, so f prime, minus the high, which is f, d low is g prime, and then all over low low just means we square the low function. G times g is g squared. So if we were live in person right now, I'd have you repeat after me, low d high minus high d low, all over low low. And then finally, in this general rules section here, we have the chain rule. And so the chain rule is going to be f prime of g times g prime. Now you'll notice I'm leaving my x's off. I hope that doesn't bother any of you. Textbook version would be like f prime of g of x times g prime of x. If you're more formal, you might want to write it like this. I tend to write it how you see here, just again, to simplify it a little bit and make it a little bit easier to remember for you guys. Then down at the bottom of this same page, we have the trig derivative rules. And so with the derivative of sine, we know that's cosine. Derivative of cosine is negative sine. derivative of tangent is secant squared x. All of these things should go on your yellow sheet, my friends. You should make note cards so that you make sure you memorize for the exam. And then for cosecant, it's negative cosecant x cotangent x. And then secant is secant x tangent x. And then finally for cotangent, we have negative cosecant squared x. And I would make a note here that if you're taking the trig function of anything other than plain old x, you really want to make sure that you apply that chain rule. Okay, so I'd make a little note. I usually tell my students, anytime you take the derivative of a trig function, just think chain rule, because you're going to have to chain the derivative of that inside function onto the end. Okay, so think chain rule with trig derivatives. All right, moving on to some examples. We'll look at example 4. I'll zoom in a little bit here for you. Oh, good question in the chat that I would like to just stop here for a minute and address. When do you use d by du and use u, any quantity? That's sort of what I was talking about with the chain rule. So these are all just the basic rules for the trig derivatives. But if you were using, if you were thinking about u can be any expression of x involving x. Okay, so if I had let's say sine of 2x, in this case, my u is 2x. And so if you apply chain rule here, that takes care of that. And we take the derivative of the outside function, f prime is cosine, since the outside function is sine. Inside function is 2x, so we keep it the same, but then we have to chain on the derivative of the inside function to the end. Cool. Okay. Yeah. Thank you for that.
So Melanie,
go ahead.
Maybe write just really quickly. So like in where it says d over dx sine x, if they were using u's, it would say sine u, and then it'd be what, du over dx, if you wanted to write it in a term using u's.
So just write it in here. Is this what you want me to do?
Yeah, just you don't have to do them all, obviously, but and then the chain rule part would be what, du over dx for that.
Yeah.
Yeah.
Is that okay? All right. Awesome. Thank you for that question. Thank you so much. I appreciate it. Okay, so let's look at, how about we come down here and look at, let's do number 6. It's pretty challenging in that it has a product and a chain rule involved. And I say there's a little trick to it. It's not really a trick. When you're writing it in this form, to get it in the form of one of the answers, I know students tend to start simplifying their answer, and sometimes it's hard for them to get the answer in the form that it's presented here on the multiple choice question for the AP exam. So let's look at number 6 on page 5 together. Number 6 on page 5. So for this one, as I already mentioned, we do have a product rule and we have a chain rule going on. So I'm going to say that I'm going to start with my product rule here. And for my product rule, I'm going to call this my F and this whole thing here is going to be my G, and that's how I'm going to get started. And I'm going to do GF prime plus FG prime. But when I get to the G prime part, I'm going to have to do chain rule. Okay, so let's dig in and get our product rule here, which is G times F prime is 1 plus F times G prime. Now, G prime is where I need the chain rule because I have a composition function. I oftentimes have students ask me, when do we do the chain rule? How do we know? We know it's a chain rule when you have a composition function, meaning when you have one function inside of another function. One of my very best friends that teaches BC here at my school, she calls it a pregnant function. She says when you have a function inside another function, that's when you're going to use the chain rule. So we're going to do that here by pulling down the 3. I'm using power rule on x cubed, by the way, if you're used to identifying your inside and outside functions. I'm leaving my inside function alone, and then I'm going to chain on the derivative of the inside to the end. So this here, my friends, this whole thing that you're seeing, that is G prime. That is G prime. So we have GF prime plus FG prime. And now here's where students tend to want to start, multiplying everything together. But what we're going to do is I want you to look at this as 2 separate terms. So you've got one term here, and I want you to look at this as a separate term. Remember, terms are typically separated by plus or minus. If you look at these 2 separate terms, I want you to think about what the GCF would be. And we're going to pull out the GCF. So the GCF would end up being x squared plus 2 quantity squared. Both of those terms have that in common. So I'm going to say x squared plus 2 squared. And then I'm going to open up a bracket, which in this context means nothing different than a big old parenthesis. And it leaves me with x squared plus 2 in the first underlined term. And then, let's go right down. Plus the x minus 1 times 3 times 2x. So that's what I was talking about at the beginning about a trick to it. It's not a trick. It's you're factoring out the GCF, right? Once you complete the calculus, it's the algebra that sometimes gets us. So make sure once you complete the calculus, you pull out the GCF. And my hint here, the reason I knew to sort of do that is I looked over at my answer choices. It's always good to look at your answer choices to kind of see what form your answer should take. And it looks like my answer is in factored form. So that's why I was clued in, hey, let me pull out this GCF and see what happens. So let's simplify inside. And I get x squared plus 2 plus, x squared plus 2. Let's go ahead and make this 6x and distribute that in to be 6x squared minus 6x. And then once you combine like terms, you should have 7x squared minus 6x plus 2. Notice I went back to parentheses after I got my simplification down. And so it appears that our answer matches up with letter D on this one. Letter D. All right, please let me know if you have any questions about that in the chat. And we will move into, oh boy, I would love to do number 7 with you. Let's look at number 7, and then we'll have time to do part of that implicit differentiation there at the end. So number 7 is h of x equals f of x times g of x plus f of x divided by g of x, and they want us to find the value of h prime of 5. H prime of 5. So I know I'm going to use my derivative rules here, and what I'm seeing is a product and a quotient. So I'm going to do product rule and quotient rule. So h prime of 5, if you write it out, I'm going to write it out shorthand here. I'm going to do product rule. I'll do that here in pink. So I'm going to do gf prime plus fg prime. And then I'm going to do my quotient rule. I'll do that in green. So I'm going to add to that gf prime plus fg prime over g squared. So low d high. Oop, that should be a minus. Oh, look at that. I would have missed that one, huh? Minus high d low over low low. And then we're going to evaluate that at x equals 5. And I hope the notation doesn't bother you too bad. Just a point here on multiple choice for the students, you can be, you want to try to, get to the answer the quickest way possible. You don't have to be very formal with your notation, especially on the multiple choice. But I'm trying to be a little better since I'm explaining it to you. But when you're taking the actual exam, you want to try to answer it as fast as you can, but also efficiently as possible, I guess I should say. So now let's do using the table. So this is a tabular problem, which is a very popular type problem. You're not given an equation, you're not given a graph, you're given a table. So we're going to do g of 5. So look up at your table. G of 5 is going to be right here at -2, or -2 is g of 5, right? You find 5 in the x column, and then you find your g of x, and you see where they intersect, and that happens at -2. So I'm going to do -2 times f prime of 5. Well, f prime of 5 is going to be 4. Then we're going to add to that f of 5, which is 3. And then g prime of 5 is 5. And I'll go ahead and finish that out. So notice that we're only using this last row here where x equals 5. You're given more information than you need. So you can kind of block out the row for x equals 3 and x equals 4 in this case. So g of 5 we said was -2. F prime of 5 was 4. F of 5 was 3. And g prime of 5 was 5. All over g of 5, which is -2. And we're going to square it. Now, once you simplify that, you should get 5/4, which is letter A. Okay, I see a question in the chat real quick. What suggestions do I have for people who almost overwork the problems? I'm thinking you mean like overanalyze maybe, or you go too far. That is definitely a skill to work on with the free response items. I think more with practice. Once you see examples of what a good response looks like, or once you start looking at the like the scoring rubric, I think that will help you in knowing where to stop on some of these problems. Now, obviously with the multiple choice, you're going to work it all the way out. But with the free response, certainly knowing when to stop is a skill that will come with practice once you practice more of your free response items. And I'm getting the cue that I only have 5 minutes left. So I really do want to get into, let me do this implicit differentiation, at least show you part A of number 11, showing dy by dx. They give you what your answer should look like, but you do have to show how you get that using implicit differentiation. So I want to give you one example of that. And before I do that, let me just say that any of these problems that you want to, after you leave this session, I encourage you to go work them out and shoot me an email, find me on Twitter, and I will be more than happy to answer your questions or check your answers for the problems that you work out. All right, so having said that, let's get into number 11. This will be a free response type question over implicit differentiation. And so we want to show that dy by dx equals this expression. It starts with xy squared minus x cubed y equals 6. And right away, my head goes to product rule because I have x times y squared. That's a product, multiplication. X cubed times y, that is multiplication. So I'm going to do product rule twice here when I do my derivative. And I'm just going to start up here, although on the exam, you want to make sure that you answer your question in the box for part A, in the box for part B, and so on. But so that I have a little more room, I'm going to start up here in this blank space, and I'm going to take the derivative using the product rule. So I'm going to start with the xy squared, and I'm going to do y squared times 1 plus x times 2y dy by dx. Now, for those of you that may have forgotten, remember for implicit differentiation, once you take the derivative of y, when you're taking the derivative of y with respect to x, you have to chain on that dy by dx to the end every time you take the derivative of a term involving y. So that's what I did there. And then I'm going to subtract off this x cubed y. So I'm going to say minus, and then I'm going to open a parenthesis because I'm going to do product rule here, and that minus gets distributed to the entire product. So I'm going to do g f prime plus f times g prime is 1, but then I have to chain on that dy by dx, and 1 times dy by dx is just dy by dx, and that is going to equal 0 because the derivative of 6 is 0. Then we want to collect the dy by dx terms on one side and move everything else to the other side. And I'm going to clean it up a little bit. I'm going to write it as 2xy dy by dx. And then this negative gets distributed, don't forget. So it's minus x cubed dy by dx equals, I'm going to move my terms to the other side. Since this one here is negative The 3x squared y is negative. When I move it over, it becomes positive 3x squared y. So I'm going to put that one first. And then I'm going to move my y squared next because it's going to be negative. So my positive 3x squared y and then a negative y squared. And then we can factor out a dy by dx from the 2xy and then minus x cubed left over. And then when you divide both sides by that parenthesis, you will see that you get exactly what it was asking you for. It was asking you to show that dy by dx is equal to that expression. All right, so again, if you have any questions about the ones that we didn't quite get to today, please, please, please feel free to contact me. I'd be more than happy to help in any way that I can. I've really enjoyed being here with you guys today. Thank you so much for participating and being attentive. And thank you to Advanced Kentucky for this opportunity.
All right, thanks, Melanie. I'm going to share my screen here really quickly.
Okay.
All right, hold on, sorry. Here we go. Oh, hold on, sorry. Here we go. All right, so just as a reminder, if you need to reach out to us, our website is there along with our Twitter, Facebook. Especially if you found today beneficial, please, please, please promote us and give us some shout outs. We'd appreciate that as well. Emails can be directed to me or Melanie, especially if you have questions or are requesting solutions to questions that were not worked today. Handouts and recordings, a reminder, the handouts can be found at the bit.ly link /mathcrs. And then today's recording, along with all future recordings as well as registration links, will be at the bit.ly/ADVKY site. So Melanie touched on this earlier at the beginning, but next session is February 6th. It will cover differentiation applications, which is unit 4, and then big theorems, which is a little bit of a hodgepodge, unit 5, along with picking up the end of unit 1. So Danielle Meyer will be covering assorted topics such as position, velocity, acceleration, related rates, local linearization, mean value theorem, extreme value theorem, intermediate value theorem. Oh my. So please tune in, spread the word, and let's see, do we have any other questions? Melanie, do you have any in yours? The recording will be at the bit.ly/ADVKY website. I can actually show you that really quick. So while I've got the screen shared here. And then Melanie, do you have any other questions that are coming up on your side?
I just have, I do have a direct message, but I'm responding now. Okay. But I think we're good on questions.
All right. So again, here is the bit.ly site. And then to see the recording, if you click on calculus, it will show up on this screen here. So right below where you all registered, we will embed the video there. So that's where you can go, as well as all future sessions that are already posted along with registration links. So please make sure you're taking advantage of that. So if there are no other questions, we will let you have the rest of your Saturday. Thank you again, Melanie. You did a great job. Very appreciative to you and your hard work putting into this. All right, take care, everyone.
Bye, everyone.